41st Houston Lecture. William V. Houston came to Rice in 1946 from Caltech to serve as Rice's second president. He was a distinguished scientist, known particularly for his work on spectroscopy and condensed matter theory. As a graduate student, he had studied with Michelson and Millikan at the University of Chicago. During a Guggenheim Fellowship in 1927, he did early work with Sommerfeld and Eckhart on calculating the electron mean free path and the theory of conductivity in metals. During World War II, he worked on undersea warfare, for which he was awarded the Navy Medal of Merit. He was elected to the National Academy of Sciences in 1942 and was president of the American Physical Society in 1962. He retired from his position as Rice's president in 1961, but continued to be active in teaching and research until his death in 1968. Following his death, this lectureship was established to honor his important contributions to 20th century physics, and in particular, his role in the development of physics at Rice University. I would now like to pass the microphone to Professor Mustafa Amin to introduce today's speaker.
Thank you, Tom. So it's a real pleasure and honor to introduce Professor Alan Guth. So Alan is the father of inflationary cosmology. His ideas have really allowed us to connect what we see in the sky today to what happened right at the beginning of the universe. His ideas allow us to really have a testable, calculable framework in which we can address our origins. Alan's impact is enormous on the field of cosmology, and to see this, you can just look at the number of observational probes as well as theoretical effort that's ongoing to really constrain this inflationary paradigm. So Alan got his undergraduate and graduate education from MIT. After that, he had postdocs at Cornell, Columbia, Princeton, and the Stanford Lunar Accelerator, after which he returned back to MIT as an associate professor, and he's been there ever since. He is currently the Victor Weisskopf Professor of Physics. Alan has been very widely recognized for his contributions to cosmology. He's won the Eddington Medal, the Isaac Newton Medal, the Dirac Medal, and more recently, just to name a few of them, the Kavli Prize, as well as the inaugural Nobel Physics Prize. So one thing I've known about Alan is that he has incredibly uncluttered thinking. But this did not stop him from winning the Messier's Office Award from the Boston Globe. So oftentimes, I walked into his office with cluttered thinking, and I would come back with a level of clarity. And I've heard the similar things from many of my colleagues as well. I suspect that might have something to do with the clutter in his office. So Alan's contributions beyond just his papers, he's been a fantastic mentor and an educator. Beyond his graduate students and postdocs and so on, he still continues to mentor a dozen undergraduate students over the past 2 years. Coming back to his research, I think the most profound impact I find of Alan's work is that it provides a framework for asking questions that we haven't even thought about being possible. It is one such question, a question about the multiverse, that Alan will address today. So with that, please join me in welcoming Professor Alan Guth.
Thank you so much, Mustafa, for that lovely introduction, which I'll try to live up to, but we'll see. In today's talk, I want to discuss inflationary cosmology as advertised, and I intend to divide the talk into roughly 3 sections. First, I'd like to describe what inflation is and how it works. Second, I'd like to give you a brief summary of the evidence that our universe actually went through this process called inflation. And then third, I will get to this multiverse issue, which is in the title. The possibility that inflation gives rise not just to one universe, but to a whole set of possibly even an infinite number of universes. And that's certainly speculative, But I will explain to you why I think it is something that we should take seriously, at least as a possibility. So I want to begin at the beginning. This, by the way, is a picture of the Planck satellite. I'll be talking soon about some of the evidence that the Planck satellite has garnered for us. But I want to begin at the beginning, so I'll start by talking about some features of the conventional Big Bang theory. That is the theory that was present before inflation was proposed. So that theory is essentially the theory that the universe, as we know it, began some 13 to 15 billion years ago, and now we even have an incredibly accurate number for that age. It's 13.82 plus or minus 0.05 million years since the beginning. The initial state was a hot, dense, uniform soup of particles that filled space uniformly and was expanding rapidly. Now, when I say it filled the space uniformly, you should realize that that contradicts what is a standard cartoon image of the Big Bang. A very common cartoon image is that the Big Bang was an egg that was sitting in empty space and exploded. That was never the scientific version of the Big Bang theory. It's just as logical as the scientific versions, as far as I can tell, but it doesn't fit the data as well. Because when we look around the universe, what we see is that it pretty much looks the same in all directions, especially if you average over large scales. While if it was an egg that exploded, unless you were right at the location of the egg, you would not expect that. You'd expect to see something that looks hotter if you look where the explosion took place, and then you'd see if you looked in the opposite direction. So the egg theory doesn't work very well as far as agreeing with what we see. So instead, in the conventional version of the theory, we just assume that everything was uniform from the start. We'll come back later to talk about what inflation has to say about that. The Big Bang theory describes how the early universe expanded in pools. It describes how the light chemical elements form. In saying that, I should clarify that the Big Bang picture begins at a time that was so early that the universe was so hot that even the nuclei of atoms would not have been stable. So the nuclei that we see in the universe today have to have formed since the Big Bang. There was a time when physicists were trying to explain the abundances of all the chemical elements in terms of what would have been produced in the Big Bang. That never worked. And we now believe that only the lightest chemical elements, the first few isotopes of hydrogen, helium, and a little bit of lithium, were produced primarily in the Big Bang, and that all the heavier elements that we see were produced much later in the history of the universe in the interior of stars, which later undergo explosions, spewing these heavy elements out into space to collect into later generation stars, such as our own sun. Finally, getting back to the middle of my sentence here, the conventional Big Bang theory describes how structure formed in the universe. From gravitational clumping. What's most interesting for today's talk is what the conventional Big Bang theory does not describe, so I'll move on to that. One of the things it does not describe is what caused the expansion. In spite of the fact that this theory is called the Big Bang theory, in fact says nothing about the bang. It is really, truly only the theory of the aftermath of the bang. And I like to say that it says nothing about what bang, why it banged, or what happened before that. It is really a bangless theory. So inflation helps to fill in some of those gaps, at least as a very plausible explanation. Secondly, the conventional Big Bang theory says nothing about where all the matter came from. The theory assumes that all the matter was present in the sense that from the very beginning, for every particle that exists in the universe today, there was at least a precursor particle that eventually became that particle. Inflation will also provide a more interesting answer to that question. So that's all I wanted to say about conventional Big Bang theory. Now I'll start talking about inflation. Inflation is essentially a theory about the bang of the Big Bang. That is, it's a possible answer to the question of what propelled this gigantic expansion, which is still governing the way the universe is evolving. And before the possibility of inflation, Big Bang theorists really made no attempt whatever to explain the bang of the Big Bang, what caused the expansion. Inflation explains this expansion by the use of gravitational repulsion. Now, depending on how familiar you are with these things, you may say gravitational repulsion, what's that? Certainly in the context of Isaac Newton, gravity was entirely attractive. So I like to think of gravitational repulsion as a miracle of physics. And I will advertise that inflation is essentially the product of two miracles of physics. And I should define what I mean by miracle. I'm not referring to anything that's supernatural, but my definition of a miracle in physics is that it's a feature of the actual laws of physics as we understand them, which has two properties. One is the negative property when I just use it, and that's certainly true about gravitational repulsion. And secondly, it's so far-reaching in its consequences that it can really change our view of the universe and how it evolved. So this defines what I mean by a miracle of physics. And as I said, inflation will be based on, the way I would describe it, will be based on two miracles of physics, the first of which is gravitational repulsion. Gravitational repulsion has been present in physics actually since the advent of general relativity. Newtonian gravity is purely attractive, but general relativity offers the possibility of gravitational repulsion. And I wrote here in gray something that's a little bit more technical than the rest, but if you don't understand the gray part, that's okay, it won't be necessary for the rest. But in general relativity, the key thing that allows gravitational repulsion is the fact that in general relativity, pressures, as well as energy densities, contribute to the source of the gravitational field. And energy densities, so far as we know, are always positive and always produce attractive gravitational fields. Positive pressures also produce attractive gravitational fields, which is probably what you would guess if you had to guess. But pressures can be negative, and negative pressures produce a repulsive gravitational field. In the case of inflation, this negative pressure arises because of fields that are used in the field theory that underlies inflation. But just to understand what negative pressure means, you can even just imagine a piece of rubber that you stretch out in all directions, so it's pulling back in all directions. That would be a negative pressure. Not large enough for us to measure the repulsive gravitational field that it takes, but it would, according to general relativity, create a small repulsive contribution to the gravitational field, although it would not overcome the attractive gravity of the mass. So GR allows the possibility of repulsive gravity, and in fact, Einstein himself used it very early on in 1917 in his first model of cosmology, where he introduced what he called the cosmological constant. And this cosmological constant really corresponds to a negative pressure material in modern language. And he introduced it because he wanted to build a static model of the universe. The expansion of the universe had not yet been observed. And Einstein assumed with pretty high degree of certainty on his part that the universe must be static, and tried hard to build a static model of the universe. He first discovered that general relativity in its original form would lead to attractive gravity, which would cause everything to collapse. A static model was not possible until he added this repulsive gravity component arising from this cosmological constant. In modern particle physics, the suggestion, and that has been what you get if you just extrapolate what we know about particle physics to high energies, is that at super high energies there should be many states of matter with negative pressures creating this repulsive gravity. And that's what inflation relies on. So the story, as a chronology, is that inflation proposes that at least a patch of this repulsive gravity material existed in the very early universe. It doesn't have to be the whole universe, a small patch suffices. Inflation could have happened at many different energy scales as far as we presently know. So the numbers that I will give you will be plausible numbers based on the idea that inflation happened at the grand unified theory scale. It could have happened at somewhat lower energy scale. The numbers would be somewhat different. They would all have the same flavor as the numbers that I'm showing, although they could differ by many orders of magnitude, actually. But if inflation happened at the grand unified theory scale, this patch would only need to be as large as 10 to the minus 28 centimeters. And we should remember that since this patch is going to be enlarged fantastically by inflation, it doesn't really have to have an initial, the density of such patches does not have to be high, or the probability of informing does not have to be high. As long as there's at least one of them, that will in the end dominate over everything else after the exponential expansion. So once one has a small patch of this repulsive gravity material, it will start to exponentially expand, driven by the gravitational repulsion. That will become the driving force behind the Big Bang of that little patch. The patch will expand exponentially with a doubling time that would be in the neighborhood, using grand unified theory numbers, of about 10 to the minus 38 seconds. Every 10 to the minus 38 seconds it will double and then redouble and then redouble. To give enough inflation to make this work, the patch has to exponentially expand by a factor of about 10 to the 28. And that corresponds to about 100 doubling times. So 100 is not that large a number. It could have expanded much more. There's no upper limit to how much inflation our universe might have undergone. It doesn't cause any harm if too much happens. It just makes the universe bigger and bigger beyond what we can see. At the end, the region destined to become the presently observed universe would be about the size of a marble, about a centimeter or so across. The expansion does not stop there. The accelerated expansion stops there. The gravitational repulsion turns off at that point. But then this little marble continues to coast outward in what we normally call the Big Bang. What causes inflation to end is that this repulsive gravity material is unstable. So it decayed pretty much like a radioactive substance. And that ended the inflation, it ended the period of repulsive gravity. When that decay happens, it releases energy, the energy that had been locked up in this metastable state. And that energy that's released then creates all kinds of different particles, which rapidly reaches a thermal equilibrium mixed, which is the hot primordial soup of the dimensional Big Bang theory. So at the end of inflation, we have set up the initial conditions for the conventional Big Bang theory to take over. And that's really the role of inflation. It's a prequel to the standard Big Bang theory. So all of the successes of the conventional Big Bang theory get to be preserved, but inflation explains many features which previously we just had to build into the initial conditions, and now instead we can explain them. A key feature that's crucial to making all of this work is that during the exponential expansion, the density of matter and energy in this region did not thin out, which is very peculiar. Normally, if you have a gas or something in a vial and you expand the volume of it, the gas thins out. But that did not happen during inflation. The energy density inside this exponentially expanding region was maintained. Since the energy density is maintained while the volume increases by a huge factor, it means that the mass energy of the material in this region increases by a huge factor. And that leads to the question of what's happening to conservation of energy. You might sense that now it's time for my second miracle. Second miracle is that this does in fact conserve energy. Because although energy is conserved, it has a peculiar property, contrary to, I think, what most of us have been brought up to believe, that energy is not always positive. And in particular, the energy of the gravitational field is negative, a statement which is true both in Newtonian physics and in general relativity. In classical mechanics courses, it's not usually taught that the energy of gravity is negative, but it is. So what's happening during inflation is that more and more positive energy is appearing in the form of this ever-enlarging region with a large energy density. But at the same time, more and more negative energy is appearing in the gravitational field, which is filling this region. So the total energy is constant, and it's very possibly zero. There could be a perfect cancellation between the positive energy of matter and the negative energy of gravity. And if the cancellation is not perfect, it's at least very good. The total energy of the universe that inflation leads to is incredibly small, if non-zero. Have a little schematic to sort of drive that point home. The total energy of the universe has a large positive contribution, shown in black, consisting of the matter and radiation that fills the universe today. But it also has a large negative contribution, shown in red, from the gravitational field that fills the universe. And the total is consistent with being zero. We don't know that's really zero, but the total is consistent with being zero. So contrary to what you might think, it does not take a huge amount of energy to build the universe. In fact, it might not take any energy at all. Okay, that completes what I wanted to say about how inflation works. And now I want to move on to the second phase of my talk. I want to describe some of the evidence that leads us to believe that our universe, at least very likely, did undergo this process called inflation. So there are basically three items I want to talk about, and then the fourth I'll say a little bit about, which is not at this point evidence yet. But the three I want to talk about, the first of those is the large-scale uniformity of the universe. The fact that if you look at the universe on large scales, it's the same everywhere we look. And this fact is seen most clearly in the cosmic background radiation, which is known to be uniform in its temperature, or equivalently in its intensity, to 1 part in 100,000, which, if you think about it, is really incredibly uniform. Now, to understand why this is a problem, I need to say a little bit about the history of this radiation. We think of the radiation as having been released at about 380,000 years after the Big Bang. What I mean by released is that prior to that time, the universe was so hot that the matter that filled the universe was in the form of a plasma, mostly hydrogen plasma, protons and electrons. It turns out that a plasma is very opaque to photons, very non-transparent. So the cosmic background radiation photons were present during this early period, before 380,000 years. And they were traveling at the speed of light, because photons always travel at the speed of light. But they were constantly ricocheting off of mainly the free electrons of plasma. And therefore they changed their direction incredibly rapidly. So the net effect is that even though the photons were instantaneously moving at the speed of light, because of the rapid changes of direction, the photons didn't go anywhere during the first 380,000 years. So you can think of the photons as being locked to the rest of the matter during that first period. But then, in about 380,000 years, the universe finally cooled enough so the plasma neutralized, and the neutral gas that formed was highly transparent to photons. So the photons that we see today in the cosmic background radiation were by and large traveling on straight lines from 380,000 years until today. And because they were traveling on straight lines, they really give us an image of what the universe looked like at 380,000 years. Exactly like the light traveling from my face to your eyes tells you what I look like. So we're really seeing a picture of what the universe looked like at 380,000 years. And then we could ask ourselves, was there enough time for the universe to come to a uniform temperature and matter density by 380,000 years? And the answer to that question really only involves a pretty quick calculation once one understands the basics of cosmological evolution. And it turns out that the answer is a resounding no. There was not enough time for the universe to make itself uniform. And in fact, in order for the universe to make itself uniform that quickly, one would have to require information and energy to be transmitted at about 100 times the speed of light. And as far as we know, nothing travels faster than light, so it's just not possible. Now you could, of course, still, since we don't really know how the universe really was created, you could assume that the universe just started out completely uniform, and that would be okay. But if you want to explain that uniformity by any dynamical process, then it's just not possible with conventional cosmology. But inflation changes that dramatically by changing the expansion history of the universe. In the inflationary model, we've modified the story by adding this period of incredibly rapid exponential expansion. And what that means is that if we look today at the region that comprises the presently observed universe and follow it backwards in time, it gets smaller and smaller. And when we followed back through the period of inflation, where there was incredibly rapid expansion going forward or contraction going backwards, by the time we get to the period before inflation, it's unbelievably tiny compared to anything that was imagined in conventional cosmology. So in an inflationary model, this uniformity can be established very naturally before inflation starts on this very tiny length scale. And then inflation takes this uniform, tiny, tiny region and expands it to become large enough so that today it includes everything that we see. So inflation gives a very natural and simple explanation for how the universe could have gotten to be so amazingly uniform. Okay, the second item I want to talk about is usually called the flatness problem, which the phrase might not make much sense right now, but I'll explain what it means. The question basically is, why was the early universe so flat? Where flat refers to Euclidean geometry, and certainly does not mean two-dimensional, that's the word flat. And the key facts behind this is that if we assume that the universe is homogeneous, the same in all places, and isotropic, the same in all directions, as far as we can tell, those are accurate descriptions of our universe, not exact, accurate. Then it turns out that there are only three possible geometries, which are called closed, open, or flat. And they each have two-dimensional analogs. We're really talking about the three-dimensional space of the universe. But they do have two-dimensional analogs, which is the surface of the sphere as an analog for a closed geometry, a saddle-shaped surface, which is the analog of an open geometry, and right in between these two is a flat geometry. That's a very special case. And according to general relativity, the flatness of the universe, the choice between these three options, is governed by the mass density of the universe. Mass creates curvature of space. So cosmologists define a quantity called omega, which is the actual mass density of the universe, divided by something called the critical mass density, where this critical density depends on the expansion rate. It's not a universal constant of nature, but it's defined for a given expansion rate as that mass density which would make the universe geometrically flat. Put the universe right on the border between the closed and open. So if you think about how to put all this together, it means that omega equals 1 corresponds to a flat universe, omega greater than 1 corresponds to a closed universe, and omega less than 1 corresponds to an open universe. We're basically trying to explain why omega is something like flat, why it's somewhere in the 1. I'll be a little bit clearer about that on this slide. It turns out that the universe at its critical density is much like a pencil balancing on its tip. It's an unstable equilibrium point. If the pencil is exactly straight up, then at least according to the laws of classical physics, it will remain straight up forever, so it won't know which way to fall. But if the pencil is leaning just the slightest bit in any direction, it will rapidly start to fall in that direction. And the universe is pretty much the same way related to omega equals 1, where omega equals 1 is like the pencil being straight on its tip. If the universe had a value of omega at early times which was slightly below 1, it would rapidly fall to 0. And no galaxies would form in that case. It would really be a very different universe from what we live in. And if omega in the early universe was slightly greater than 1, it would rapidly rise towards infinity, which corresponds to the universe reaching a maximum size and turning around. And the universe would then be collapsed, and no galaxies would form. To be quantitative, to be as close to the critical density as we measure today, at 1 second after the Big Bang, omega must have been equal to 1 to 15 decimal places. Really an extraordinary amount of fine-tuning. And this flatness problem is the problem of what made omega start out so close to 1. Because in conventional cosmology, any value would do as far as being consistent with what we know about how the universe formed. Only omega incredibly close to 1 gives us a universe which ultimately looks like what we see today, but we should be able to explain what the early universe looked like in terms of the early universe, not the other way around. We don't think of today's universe as causing what happened in the early universe. So we need some early universe explanation for why omega started out so extraordinarily close to 1. And that's the flatness Inflationary cosmology gives us a wonderful solution to it, it turns out. Since inflation makes gravity become repulsive, lots of things change, including the evolution of omega. And it turns out that during the inflation, omega, in fact, is driven towards 1 instead of away from 1, and it's driven towards 1 incredibly rapidly, exponentially fast. So if we had the amount of inflation that I described, 100 doublings, that would mean that before inflation, omega didn't have to be 1 to 15 decimal places. It didn't even have to be 1 to 1 decimal place, or even 0 decimal places. It could start out at 10 or 10. The further away it starts from 1, you need a little bit of extra inflation to drive it close enough to 1 to be consistent with what we observe. But the initial value of omega really couldn't have been anything. And the amount of inflation I talked about, anything of order 1, 10 or a tenth, would be just fine. So this also leads to a prediction. The mechanism that drives omega to 1, that explains the problem, almost always overshoots. The only way to allow it not to overshoot is to have inflation stop at just the right moment before you've made the universe flatter than you needed to. And that really requires a lot of fine-tuning. So in almost all models of inflation, omega is driven so close to 1 that today you'd expect it to really be at 1, and now it's just near 1. So that's a prediction of almost all inflationary models, that omega should not be merely near 1 today, it really should be equal to 1, or at least a very high degree of accuracy. Now, in the old days, before 1998, observations were pointing towards the value of omega of only 0.2 or 0.3. Now, on a personal note, I can say that this made it somewhat uncomfortable for me during this period to have dinner with astronomers. They would sneer at me and tell me that inflation was a beautiful theory, but couldn't actually be right because the universe has omega of 0.3, and the theory predicts omega should be 1. So obviously it was really a no-go. It's a cute theory, but wasn't really going to turn out to describe the universe. But that all changed in 1998, and now the latest observation of omega, which comes from the Planck satellite team combining the data with some other astronomical observations, is that the observational value of omega is 1.0008, plus or minus 0.004. Actually, the uncertainty is more important than the value here. Roughly speaking, we know that the universe is flat of omega equal 1 to an accuracy somewhat better than 0.5%. And this is a 95% confidence measurement. So it's really unbelievable how much data has meant to cosmology in recent years. It is really becoming a precision science. And the precision is telling us that indeed omega is at least unbelievably close to 1, as inflation predicts, which is gorgeous. The new ingredient that makes omega 1 instead of 0.2 or 0.3 is the dark energy, and that's why 1998 is an important date. In 1998, many of you may know, astronomers discovered, two separate groups of astronomers announced, that by measuring distant supernovae of type 1a, they could trace the expansion history of the universe and determine that, in fact, the universe has not been slowing down under the influence of gravity, but for approximately the last 5 or 6 billion years, the universe has actually been accelerating. Which basically means that the universe today is filled with a repulsive gravity material, which at least in its general character is similar to what we're talking about as having driven inflation in the early universe. The inflation we're seeing today is vastly slower. It's not the same inflation. But certainly, well, within the context of general relativity, it has to be driven by a negative pressure. So we think that today the universe is actually filled with material with negative pressure, and we call that stuff the dark energy. And it's the inclusion of the dark energy that brings up the 0.2 or 0.3 to 1. So my astronomer friends who were sneering at me at dinner were right about the amount of matter of the ordinary type that's in the universe, but none of us at that time knew about this dark energy. Third item I want to talk about is the small-scale non-uniformity of the universe. On the larger scales, the universe is far more uniform than we can understand in the context of conventional cosmology. But on smaller scales, we of course see all kinds of structure in the universe, galaxies, clusters of galaxies, planets, stars, everything. And that has to come from somewhere too. I can say that in the very early days of inflation, there was a period of about a year, more or less, where I and other friends who were working on inflation were very worried that inflation seemed to lead to a universe that was completely smooth. And if it was completely smooth, there'd really be no place for galaxies to form. And we worry that there'd be no way of accounting for galaxy formation in an inflationary model. Then it was realized by several different sources that quantum theory can come to our rescue. It turns out that these quantum uncertainties are exactly what we need to produce ripples in the early universe. That is, if the classical physics, just due to stretching, predicts an almost perfectly uniform distribution of matter in the universe after inflation, a quantum theory, simply because of the uncertainties intrinsic to quantum theory, will predict that in some places the mass density will be a little bit higher than that classically predicted average. In other places, the mass density will be a little bit below that classically predicted average. And that is precisely the kind of ripples that we think must have been in the early universe, and that we now see very directly in the cosmic background radiation. The intensity of this cosmic background radiation has now been measured very sensitively. I mentioned earlier that it's uniform to 1 part in 100,000, which is amazing. But there are actually non-uniformities seen at the level of 1 part in 100,000 that are now measured to extraordinary precision by marvelous experiments such as this long satellite that I showed you the picture of at the beginning. So inflation attributes these ripples to quantum fluctuations, which is amazing. It means that the Andromeda galaxy exists because of quantum theory, which is mind-boggling, really. And as a consequence of this idea, the precise predictions differ from one version of inflation to another, and we still have many. But nonetheless, there are generic features that all of the simplest models of inflation obey. And in particular, this, just knowing that we're talking about one of the class of the simplest versions of inflation, we can make predictions for the spectrum of these primordial fluctuations. And by spectrum, what I mean is pretty much what we mean when we talk about the spectrum of a sound signal. It means how the intensity varies with wavelength. With sound, you might think of frequency. Here we don't really want to think about frequency because we don't see it oscillate. What we see is a pattern on the sky. But we can break up what we see into components of definite wavelengths on the sky and talk about how the intensity varies with wavelength. And that's what we mean by this spectrum. The spectrum that's predicted by inflation is a marvelous fit to what's observed. First, I just showed here what the data looks like. And this is the data from the Planck satellite. This is really just a picture of the sky showing the intensity of the cosmic microwave background in each position in the sky. And I should emphasize that this is a false color picture. The actual variations are less than 1 part in 100,000. There's a scale on the bottom which goes from minus 300 microkelvin to plus 300 microkelvin. And the colors that are at the edges, you don't see very much of, in fact, in the actual diagram. Mostly between about minus 100 to plus 100. And it's now measured to incredible precision. Now, it's hard to make much out of this picture, but this picture can be used to calculate a spectrum, how the intensity varies with wavelength by literally breaking that picture up into components that have definite wavelengths. And that's the skygram. Now, what's shown here is the intensity of the temperature fluctuation in microkelvin squared, which is the square of the fluctuation being plotted here, versus the angular scale, the wavelength, measured as an angle. We don't know the actual physical size, because we don't directly measure it, estimate. But what we directly measure is the angular size of these fluctuations, and that's what's plotted. Where the shortest wavelengths are at the right, and the longest wavelengths are at the left. And the green line is the prediction of the simplest inflationary models with a few parameters fit to the data. It's not quite a blind fit. But there are really only 2 parameters that are fit pretty blindly, and I can maybe mention those. The overall height here is fit to the data. Inflation does not at least our present understanding of inflation, is not sufficient to really predict the exact amplitude of these fluctuations. So the amplitude, in fact, that fits perfectly, it's just the right height, that's fit to the data. But the ratio of these to each other, that really comes out of the theory. There's one other parameter that's fit purely to the data, which is a parameter that goes into the calculation which describes the extinction of the cosmic background radiation from the time it's released to the time we receive it. That's, I think, estimated to be something like 6%, and it comes purely from this bit. There are other parameters that come here, but all the other parameters are parameters that really can be checked with other kinds of observations. And they agree very well. So those couldn't be put into other observations, although here they are fit to the data. But as you see, it's an absolutely marvelous fit. And this is actually the 2013 data. There's now 2015 data, which is even better. I didn't have a good plot of it, so I didn't bring it. But it looks almost, actually, it looks identical, except all these little dots are now, you see error bars here. In the 2015 data, the circles have the same size, and there's no error bars. The error bar are the size of the circle now, and still fits absolutely gorgeously. Really, just unbelievable. I thought I'd summarize some of the conclusions that people have drawn, people other than me, about the experimental success here. In a report of the Dark Energy and C&D Working Group of the American Physical Society, they concluded that current measurements of the cosmic microwave background and observations of the large-scale distributions of dark matter and galaxies in the universe are in stunning agreement with the concept of inflation. And this Planck team, in their summary paper, which is their cosmological parameter paper from 2015, says that the Planck results offer powerful evidence in favor of simple inflationary models. Gets a little technical here. Would provide an attractive mechanism for generating the slightly tilted spectrum of nearly Gaussian adiabatic perturbations that match our data with such high precision. These words describe the graph. I showed you. Somewhat technical language. So huge success with inflation agreeing with the fluctuations that are actually observed in the cosmic background radiation. Okay, now I'm going to move on to, I'm sorry, one thing I want to comment on, because I'll mention. So one other possible piece of evidence that in fact came and went away was gravitational waves, which some of you may have heard about 2 years ago in 2014, when I have all this on the slide. On March 17th, 2014 to be exact, the BICEP 2 team had a very well-publicized press conference at the Harvard Center for Astrophysics announcing that they had detected scrolling patterns called B modes in the polarization of the cosmic microwave background, which are a beautiful fit to what we expect from inflation. And this was announced with incredible experimental validity, statistical significance, I should say. After accounting for the best estimate of contamination due to dust, they found a value for something called R, which is a measure of the strength of these gravity waves. They found a value of 0.16 errors, and these errors are small enough so that R equals 0, the absence of gravitational waves from the early universe, was disfavored at 5.9 standard deviations. And roughly speaking, that translates to the probability of the observation being statistically wrong is only about 1 in a billion. But turned out they weren't right. It gradually became revealed over the next year, starting really a month or two, that there was significant contamination in their observations simply from dust in our own galaxy. And the final conclusion was announced about a year after the original announcement, April 14, 2015, in a joint analysis by the BICEP 2 team with the Planck team. And the final conclusion was that they find strong evidence for dust, and unfortunately no statistically significant evidence for tensor modes, which means for gravity waves from the early universe. Now the search for these B modes is still going on. This is not really the end of the story. And they still might be seen, even though they weren't seen in that original experiment. We do expect them, at least many versions of inflation predict that we should see them soon, although there are also versions of inflation that predict that we'll never see them. So either is really still a possibility on the theoretical front. The search is certainly going on, and if they are found, they would not only provide strong additional evidence for inflation, but they would also be a very important tool for probing the details of inflation. So it would be a marvelous thing if these B nodes could be found. The current limit on this thing called R, which measures the strength of these B nodes, is 0.07. The hope is that we can get much better. The claims of the people who are planning future experiments is that if R is bigger than 0.001, it will in fact be found by about 2024. Have to think ahead for these kind of things, and I'm not really used to thinking that far ahead, but 2024 on the overall scheme of things is not really that far into the future. What's called CMB stage 4. If the BMOs are not found, I do need to point out here, there's not really any evidence against inflation because there are plenty of inflationary models that predict values of R significantly smaller than 0.001. So if they're found, it's great. If they're not found, it just means that we've excluded some range of models of inflation, but we certainly have not excluded inflation. Okay, now I'm ready to move on to the third phase of my talk. Which is talking about what inflation has to say about the multiverse, the possibility that our universe might not be unique at all, but might in fact be one of many universes making up this larger system, which we refer to as a multiverse. So it turns out that almost all detailed models of inflation lead to a phenomenon called eternal inflation, and that in turn leads to a multiverse. Roughly speaking, one can say that inflation is driven by a metastable state, this repulsive gravity state, which ultimately decays. And roughly speaking, it decays with some half-life, like other metastable states. But what makes this situation strange is that while the state is decaying, it's also continuing to exponentially expand. So if you wait one half-life, if you look at a region that's inflating, and you wait one half-life, then really by definition, at the end of the half-life, half of the inflating material would have become normal non-inflating matter, would have decayed, as long as it's used, to non-inflating matter. But the half that remains has continued to inflate exponentially, and it would in fact be vastly larger than it was at the beginning. So if you watch the system evolve for a half-life, half of it is no longer inflating, but the half that was inflating is now vastly larger than what you started with. So the volume of the inflating region has increased, and in fact increased dramatically, in spite of the fact that the material is decaying. And if you think about what happens if you iterate that, it just gets bigger and bigger and bigger. In the context of this model, which seems realistic, inflation goes on forever, producing more and more pocket universes. In the places where this repulsive gravity material turns normal, those regions would undergo an evolution very similar to our own Big Bang, and these local Big Bangs would produce local universes. Those local universes tend to be called pocket universes. The word pocket is just supposed to suggest that it's not a universe in the sense of everything that exists. It's a universe in the sense of everything that evolves from a single Big Bang explosion. And there'd be many of these Big Bang explosions. Each of them would be universe size. We would be living in one of them, and we would think it's everything that exists. But beyond that, if this theory is right, there's much more that also exists. So we would be living in one of these infinity of pocket universes. Okay, now does this have any relevance to anything that we might actually think about scientifically? For a long time it looked like it didn't. And I, in fact, myself was rather uninterested in the eternal aspects of inflation for some time, because I believed it looked real, but I also didn't think it in any way affected anything that we were actually interested in. But that is no longer the case. Again, starting in 1998, that magic year of transition, when astronomers discovered that the expansion of the universe has been accelerating, that turned out to lead to a whole new family of thoughts. Now, according to general relativity, this accelerated expansion requires a repulsive gravity material, which in the context of general relativity really means a negative pressure material. And whatever this stuff is, it's called the dark energy. But we really do have a good theory of what we think the dark energy is, where we includes at least a lot of the cosmological community, theoretical physics community. The simplest explanation is that the dark energy is just vacuum energy, the energy density of empty space. Now, you might think that empty space couldn't weigh anything. This is empty. What's there to have mass? But it turns out that the physicist's vacuum is really far from empty. So a non-zero energy density really is expected. The physicist's vacuum has within it constantly fluctuating fields, which fluctuate basically because of the uncertainty principle of quantum mechanics. And now we're convinced that the vacuum also has a Higgs field, which really has a non-zero value on average everywhere in space. So the vacuum is anything but empty. It's a very complicated state. And physicists don't know any reason why the energy density of the vacuum can be zero. So it makes perfectly good sense to physicists, particle physicists at least, that the vacuum energy should be non-zero. But the value that the vacuum energy has, the value that's observed from the acceleration of the universe, really makes no sense at all. We don't actually calculate the vacuum energy density, so we can't say we can calculate it if it's not that. But what we can do is estimate the natural scale for a vacuum energy. And when we do that, what we always come up with is a number of the order of what's called the Planck scale, which is the scale at which quantum gravity effects become important. It's basically the mass scale that you get from Newton's constant, Newton's gravitational constant, adding factors of h bar and c, turning it into a mass. And the value of the vacuum energy density that's observed through the acceleration is much larger. The Planck scale is much larger than the observed value by about 120 orders of magnitude. A huge amount. So we really have no understanding. It's a fantastic mystery to us why the vacuum energy of our universe is so small. So how does this involve the multiverse? Well, it turns out that the multiverse does provide a possible answer. It's a controversial answer. I'm not going to advertise it as something that you should necessarily believe if you don't want to. But it is something I think you should think about. And whether it's the right answer, I really don't know. But the first line here just summarizes where we're at one of the thorniest problems in particle theory is to understand why the energy density of our vacuum is so incredibly low, 120 orders of magnitude smaller than the Planck scale, which is what we might have expected it to be. The multiverse offers a possible, although controversial, solution. And here's how it works. Suppose there isn't just one kind of vacuum, but suppose there's 10 to the 500 different kinds of vacuum. And that really comes out of string theory. That is, string theorists estimate that the string theory itself does not have a unique vacuum, but has a huge number, possibly 10 to the 500 different types of vacuum that are all allowed out of string theory. In that case, each of these vacua would have its own energy density. And if those vacuum energies were spread between plus the Planck scale and minus the Planck scale, which is approximately what string theory would lead you to expect, then if they're evenly spread, there would still be a huge number, like maybe 10 to the 300 or something, that would have energy densities as small as what we observe. Now, 10 to the 300 is a huge number, but a tiny fraction is 10 to the 500. So that's the picture we want to have in mind here. A huge number of different kinds of vacuum, but only a tiny fraction of them have energy densities as small as what we observe. So that would allow our universe to exist within the context of this string theory model. But then we still want to try to explain why we find ourselves in such an unusual pocket universe. If only one of them in 10 to the 120 had such a small vacuum energy, why should we find ourselves in something so incredibly rare? But there is an answer to that. You may or may not find it convincing, but that's up to you. But the answer has to do with the fact that this vacuum energy is not just a number attached to the universe. It really affects the evolution of the universe in a very fundamental way. The vacuum energy determines the acceleration of the expansion. And that means that for a typical pocket universe in this picture of the multiverse, a typical pocket universe would have a vacuum energy comparable to the Planck scale. It would, if the vacuum energy were positive, fly apart in something like 10 to the minus 43 seconds. And conversely, if the vacuum energy were negative and had a value of the magnitude similar to the Planck scale, the universe would implode in something like 10 to the minus 43 seconds. So it's certainly very plausible that no matter what kind of life you might imagine, it can't form in 10 to the minus 43 seconds. Complicated structures take time to form. So it's believable that life, or anything like life, as we know it, would only form in those pocket universes with very, very small values of the vacuum energy density. So that's the hypothesis here. The hypothesis is that life only forms in those pocket universes with incredibly small vacuum energies. And then it would follow that all living things would see an incredibly small vacuum energy, even though that would be very rare in the multiverse as a whole. So that would be enough to explain our observations. And I consider it a perfectly logical possibility, although people are still looking for more dynamical kinds of explanation, which would be nice if they find one. But so far, nobody's found one. So right now, I think this is clearly the best explanation we have for why the vacuum energy we observe is so incredibly small. So I'd like to just close now. Yeah, perfect time. I'd like to close now with a kind of a survey of what physicists think, this is what a selection of physicists think, about this multiverse idea and this selection effect way of looking at things. So do physicists take this multiverse thing seriously? At a conference a few years ago, I guess a reporter went around asking people about this. So one of the people who commented on it was Martin Rees, astronomer, Royal, Great Britain, former president of the Royal Society, former master of Trinity College, all kinds of things. You can think of, he's been knighted. If you can think of it, he's had that honor. Nothing that well passed. But any other honor you can think of, he's had it. He commented that he is sufficiently confident about the multiverse to bet his dog's life on it. Now, I have to admit that I've never met his dog, so I don't know exactly what the stakes are that are involved in that. I assume his dog is very cute. It's pretty high stakes. At the same conference, Andre Linde was present. Andre is one of the other founders of Inflationary Cosmology. He shared the 2014 Cabin Prize in Astrophysics with, let's say, Starobinsky and me. And he has always been a very strong advocate of the multiverse. He commented that he was so confident about the multiverse that he would bet his own life on it. Certainly, very high stakes. Now, next comment I want to quote comes from Steve Weinberg, winner of the Nobel Prize in Physics. Also all kinds of honors that I couldn't possibly list. I've always regarded Steve as kind of the voice of reason. I've known Steve since I was in graduate school, and he's a very solid physicist. So he was not at this conference, but he commented later on what was in the press about what people said at the conference. And he said that he has just enough confidence in the multiverse to bet, if you can figure it out what he's going to say, to bet the lives of both Andre Linde and I'll stop there.
Thanks, Albert. It was a fantastic talk. We have time to take a few questions. Please wait till I bring the mic to you so you can put the mic. Hi.
So how are we supposed to think about this inflating material? What is it?
Yeah, good question. I didn't go into that in the talk because I wanted to get all in an hour. But the models of inflation that people talk about are models based on scalar fields. So I should say to anyone who's not a particle physicist here that particle physicists talk about a field to describe everything. There's a field associated with the electron, a field associated with kind of quark. It's all based on the idea that the electromagnetic field is equal to the photon. photon is sort of a quantized particle of the electromagnetic field. And now we think of all particles as being this quantized expectation of different fields. So among those fields are scalar fields. 2 years ago, I had to say we've never seen a scalar field. Now I can say we've seen a scalar field. The Higgs field is a scalar field. And the Higgs field always was the model of the kind of fields that were used in inflation. The Higgs field itself could in fact be the field that drives inflation. That is something that many papers have been written about, and it is a possibility. Most of our theories, like supersymmetric theories and string theory, predict many scalar fields. So there's certainly no reason that the scalar field behind inflation has to be the Higgs field that we know about. I'd say it's more likely not, but rather a cousin of the Higgs field. And the way it works is that you can describe most of the physics of these scalar fields by drawing a graph of the energy density of space as a function of the value of the field. And a typical graph might look something like this. They tend to be peculiar. You might think that zero field would always mean zero energy density, but that doesn't seem to be the case for scalar fields. It's certainly not the case for the Higgs field. That's our only real example of a scalar field. So inflation takes place when the scalar field in some region of space is perched on the top of that hill in the potential energy diagram. And what's special about the top of the hill is that it has the characteristics of what's often called a false vacuum. And what that means is that it's a vacuum in the sense that it's almost the lowest possible energy state. And by almost, I don't mean that there aren't states that where it's a lot lower, there would be in this model, but it takes a long time to get from the top to the bottom. So for a period of time, which is long by early universe standards, you could think of the scalar field as being stuck at the top of a hill in a potential energy diagram. And that means that the energy density is fixed at this high value. That turns out to be exactly what you need and all you need to drive inflation. Let me take it a little bit further to draw a connection to what I said before, that it's negative pressures that drive repulsive gravity and inflation. So I want to try to convince you now that we have a scalar field fixed on top of a hill, that necessarily has a negative pressure. And there are several ways of seeing it. I'll try to explain the conservation of energy that way of seeing it. Suppose, subject island, is this whiteboard? Yes. Yeah, there's a screen. Okay, right. Yeah. Back to heavy doing this. Oh, great. Also, right, see something else. Okay, so this is on this axis I have the value of the scalar field. Scalar fields are usually denoted by the root layer phi, which is one letter. And then what I'll plot is potential energy density, which I'll call D of phi. And I'm going to imagine that of something like this, which is pretty much what we think we get into. So it's not as crazy as that. Is where the scalar field actually has a value throughout some small region of space right at the top of the hill. And that means that the energy density is fixed at this value and cannot get any smaller quickly. And we will assume that everything we're talking about is going to happen fast enough so that we think of the value of the field as being frozen here at the top of the hill. And I'm going to call this state, so I'm going to draw another diagram in a second. So I'm going to call this a false vacuum. And the root of this word is that we're using vacuum in the particle physics sense of the state of lowest possible energy. It's not really that. So the false means temporary. Temporarily acts like a vacuum. So now I want to do another thought experiment, or a thought experiment. Let me imagine that I have a piston chamber that I can fill with false vacuum. And outside, I have ordinary vacuum. So I really want a vacuum with energy density equals 0, which is not exactly our vacuum. But let's pretend that such a thing exists. In any case, even if we're talking about inflation, this has such a high vacuum energy density, such a high energy density, that even if we had here our real vacuum, it's sufficiently low that it would be effectively 0. So now, what I want to imagine is that the walls of this piston are designed so that they really maintain the interior of the piston in this false vacuum state. And I want to ask myself, what happens if I pull out on the piston, enlarging the chamber in which this false vacuum exists? If the region inside is constrained to remain false vacuum, it means that the energy density inside remains constant. But the volume is going to get larger. And by the way, you can think of this as being kind of a toy model of the expansion of the universe, but I'll think of it as a system. Then the total energy inside has to go up, because there's constant density, larger volume. Now, if energy is going to be conserved, gravity could enter and confuse things, but I'm going to assume, for purposes of this thought experiment, that this is all so small, and the size that we built it at, that gravity has no effect. So it's just mechanics. And that means that if energy is going to be conserved, it's got to be that I do work by pulling out on this piston. It's the only place the energy can come from. So there's a clear conclusion that I have to do work to pull out on this piston, and you can even figure out exactly how much work I have to do. It's just what we need to enlarge this volume. And if I'm doing work to pull out, it means that there's a force pulling in, and that's the negative pressure. If this has a negative pressure, it pulls inward, and I do work by pulling outward. If this has a positive pressure, I can let it do work on me if I allow the piston chamber to go out. So the only way energy can be conserved in this experiment here is to have a negative pressure inside the piston. And in fact, you can figure out by conservation of energy that that negative pressure has to be exactly equal to the energy density in magnitude. And that's exactly how it works. So this kind of state produces negative pressure, produces repulsive gravity. And that's the more detailed version of what goes on in inflation.